In pure circular motion, the radius stays fixed, and the velocity is purely tangential. But what happens when the particle spirals outward, so the radius itself changes in time? Suddenly, the clean circular formulas break. New terms appear in both velocity and acceleration. One of them is the famous Coriolis term. Picture a particle spiraling outward in a plane. From the origin O, we draw the radial distance r out to the particle, and the angle theta measured from a fixed reference direction. At the particle, we attach two unit vectors. R hat points outward along the radius, and theta hat points perpendicular to it in the direction of increasing angle. The key new feature is this. The radial position r is no longer constant, so its time derivative dr dt is not zero. The second derivative may be non-zero too. To keep the notation clean, we drop the explicit time dependence of every quantity. Start from the position vector, which is still r hat scaled by r. To get velocity, differentiate with respect to time. Because r now changes, we need the product rule. The derivative is dr dt times r hat plus r times the derivative of r hat. And the derivative of the radial unit vector is d theta dt times theta hat. Substituting, the velocity is dr dt times r hat plus r times d theta dt times theta hat. So velocity is no longer purely tangential. It now carries a radial component. V sub r equals dr dt. That radial piece is exactly what circular motion was missing. Now differentiate the velocity to get acceleration. Apply the product rule to each piece. This gives 5 terms. D squared r dt squared times r hat plus dr dt times the derivative of r hat plus dr dt times d theta, dt times theta hat plus r times d squared theta, dt squared times theta hat plus r times d theta dt times the derivative of theta hat. Now substitute the unit vector derivatives. The derivative of r hat is d theta, dt times theta hat, and the derivative of theta hat is minus d theta dt times r hat. Collect the radial and the tangential parts. The radial component is d squared r dt squared minus r times d theta dt squared. The tangential component is 2 times dr dt times d theta dt plus r times d squared theta dt squared. Look closely at the tangential acceleration. Its second term, r times d squared theta dt squared, is the familiar angular acceleration piece you already know from circular motion. But the first term is brand new. 2 times dr dt times d theta dt appears only because the radius is changing while the angle sweeps. This cross term has a special name, the Coriolis acceleration. It couples radial motion to angular motion, and it is the reason a particle drifting outward on a spinning system feels a sideways push. Let's put these formulas to work. A particle moves outward along a spiral, starting from the origin at time 0. Its path is r equals b times theta, where b is a positive constant. The angle grows in time as theta equals c times t squared, where c is also a positive constant. We answer 4 questions. Part A, find the acceleration as a function of time. Part B, find the time when the radial acceleration is 0. Part C, find the angle at that moment. And part D, find the time when the radial and the tangential accelerations have equal magnitude. Start with part A. Substitute theta equals ct squared into r equals b theta. So the radius in time is r equals bct squared. Now we need 4 derivatives. The first time derivative of r is 2bct. The second is just 2bc. The first derivative of theta is 2ct, and the second is 2c. Feed these into our component formulas. The radial acceleration is d squared r dt squared minus r times d theta dt squared. That is 2bc minus bct squared times the quantity 2ct squared. The product gives 4bc cubed t to the 4th. So the radial acceleration is 2bc minus 4bc cubed t to the 4th. the tangential acceleration is 2 times dr dt times d theta dt plus r times d squared theta dt squared. The first piece is 2 times 2bct times 2c, which is 8bc squared t squared. The second piece is bct squared times 2c, which is 2bc squared t squared. Adding gives 10bc squared t squared. So the acceleration vector is 2bc minus 4bc cubed t to the fourth in the radial direction plus 10bc squared t squared in the tangential direction. Now part B. The radial acceleration is 0 when 2bc equals 4bc cubed t to the fourth. The bc factor cancels, leaving t to the fourth equals 1 over 2c squared. Take the fourth root. The time is 1 over 2c squared, all to the 1/4 power. Call this t1. For part C, find the angle there. The angle is c times t1 squared. Squaring the fourth root gives c times 1 over 2c squared to the 1/2 power, which simplifies to the square root of 2 over 2. So the radial acceleration vanishes at an angle of about 0.71 radians, regardless of B and C. Finally, part D. We set the two magnitudes equal 2bc minus 4bc cubed, t to the fourth equals 10bc squared t squared. Cancel the common factor of 2bc, and after rearranging we get a quartic, t to the fourth plus 5 over 2c times t squared minus 1 over 2c squared equals 0. Treat it as a quadratic in t squared. The quadratic formula gives t squared equals the square root of 33 minus 5 all over 4c. Only the positive root is physical. So the two components have equal magnitude when t equals the square root of 33 minus 5 over 4c. Three ideas carry forward. First, once the radius changes, the velocity gains a radial component dr dt along r hat, on top of the usual tangential r times d theta dt. Second, the acceleration splits into a radial part, d squared r dt squared minus r times d theta dt squared, and a tangential part, 2 times dr dt times d theta dt plus r times d squared theta dt squared. Third, that leading cross term, 2 times dr dt times d theta dt, is the Coriolis acceleration, born entirely from a moving radius. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.